Hi, in this video we'll be discussing what happens when there's complex roots for a characteristic equation. In the previous video we went through how to solve the characteristic equation when the roots are distinct and when the roots are real and equal. But what happens now when the roots are complex? Well, it is actually not too difficult as the steps and procedure to solving it is the same. So when you solve for it being complex, you will arrive at R1 equals to lambda plus I mu, imaginary mu, and lambda minus I mu. Then we can rewrite this y1 into exponential of r1 t. So r1 now is this, so it's exponential of this, and y2 will be this. So what we understand is now we treat the complex roots as distinct roots, and with that we are arrived to these complex valued functions. And we note that if the equation here are all real, then the solution of yt should be real value as well. So it cannot be this complex valued function. So we need to manipulate this function to make it in so that we can get a fundamental set of solution that is real. So how do we do that is that, well, we know that EIT, if you use the Taylor series formula, will get u equals to cosine t plus I sine t. So generalizing that, we understand that EI mu t or u mu t will equals to cosine mu t plus I sine mu t. So this is the Euler's formula, and now we have e to the power of lambda plus I mu t. So what do we do with e to the lambda times e I mu t? This we expand out using the cosine and sine, and that will arrive to e cosine mu t plus I e t lambda t sine mu t. And for y2 is similar, but here is minus. So these are still complex value function. You see, got the I. So we want the real valued version. So what we do is we just take one plus the other and one minus the other. This will lead us to this and this. And if we ignore the constants, I is just also a constant. So this is a constant. So we cancel out. We arrive to this expression and this expression only. And this will be our new set of solutions. So now we just need to check that there are fundamental set of solution. And we just check by using Abel's theorem. Or we check using the Wronskian. So we just find the Wronskian of these solutions, which is the determinant of this matrix. You arrive at mu e 2 lambda t, and you recognize that this can never be 0 because mu is not 0, e is also non-zero. Thus, this solution actually forms a fundamental set of solution for the ODE, and so the general solution now can be expressed as a real value function. So I hope you understand the procedure of solving it, as it's not too difficult. We will just see a simple example to better illustrate the point. So let's say we now want to find the solution to this IVP here, and these are the initial conditions. Then the characteristic equation will be 16r squared minus 8r plus 145. And so this will give us the roots 1/4 plus minus 3i. So the general solution will then be, if you follow this, c1 et over 4 cosine 3t plus c2 et over 4 sine 3t. If you apply the first initial condition, you see that c1 is minus 2, and by applying the second initial condition, we get that C2 is half. So this will be the solution to the IVP. And we can see how the graph looks like whenever we have such a solution, and it grows in an oscillating manner. Again, why does it oscillate? Is because of this trigonomic term over there, while the exponential term gives it the increasing amplitude. So I hope everything is clear, as it is pretty straightforward on you finding the roots and applying it to find the fundamental set of solution. I've come to the end of this video. I hope you like this video, and if you have any questions, please leave it in the comment sections down below. I will answer them, and I'll catch you again. Bye.